So number 10 on our heat quiz here is, all right, so this is final temperature. Not quite, but, so what do we got here? 50 grams of lead, and here's a specific heat of our lead at 100. Okay, so this is kind of similar to our lab. In order to get this lead to 100 degrees Celsius, water boils at 100. PV for lead. So if this is at 100 degrees, then we are going to add this to 75 grams or 75 milliliters of water. The water is at 0. So we're going to put this lead in here, transfer it. Again, this is 100 degree temperature water. This is what you're going to do tomorrow. You're going to put your metal in 100 degree water. You're going to dump this metal out. We're going to wrap paper towels around a test tube so the metal will actually stay dry because you don't want water in it. We'll wrap some paper towels around the top of the test tube. We'll dump our metal into cooler temperature water. So this water is at 0 degrees Celsius, so we know that we're going to have some Q lost equals Q gain. Now, which one of these is going to lose heat? The lead. Okay? So we know this is the lead, and we know the water is going to gain. So this is going to be mass of lead, specific heat of lead. Now, I'm going to put my temperature change in here. This is the key to the whole thing again. Let's put this in here right now, and then you'll be able to fill this in. So this lead starting out at 100, it is going to cool down, correct? It's not, obviously it's going to end up less than 100. We want the equilibrium temperature. When all of this reaches thermal equilibrium, what's the temperature? Well, this right here is going to be 100 minus T final. Because the lead starts at 100. If it goes in 0 degree water, it's going to lose temperature. So this is going to be the mass of the water, specific heat of the water. And here is our change in temperature of our water. Now, if we make this a positive value as well, what are we going to put in here? Yeah, we'd actually put in here T final minus what it started at, 0, huh?
Why is it minus plus?
It's going to, no, because typically, this isn't, usually you start this about 20, and maybe it's going to go up to 24. So it's going to be T final minus, this is really T initial. This is really T initial, right? It is a change in temperature, so we just make those change in temperatures positive values, and then everything works out.
I don't get how to, I understand all of that.
Yep.
I don't get how to solve.
Okay, let's do it then.
Yeah.
All right. So we are going to do, I'm going to double check here. Let's double check. Our units here are in kilocalories per kilogram. So let's match them up. Since this is in kilograms in the denominator, let's just make this kilograms. That'd be the easy way to do it, huh? How many kilograms here? 0.05 kilograms here. We should be all right, 0.05 kilograms. And for water, as long as we have the same unit here, we should be all right. So let's see, we've got 0.05 kilograms. The water, we can leave it in grams, it'll cancel out over here. Because right away, this kilograms here and my specific heat is going to cancel out. But it's,
Specific heat of water is 1 calorie per 100 degrees Celsius.
so if you leave it in grams, it's going to cancel out the, it would be the same, if you use kilocalories and kilograms, it would be the same. 1. We can do that. Where's our chart here? Where's our chart here? We could do it that way as well. These units on this, let me zoom in on this. Let me point this, it's good to point this out. It's the same value, because if you take this, let's talk about this right here first. If this is calories and grams, if you multiply top and bottom by 1,000 over 1,000, 1,000 calories would be 1 kilocalorie, and 1,000 grams down below would be 1 kilogram. So kilocalories per kilogram would be the same number. It actually comes out to be the same. So, and we could consistently do it that way then. So this right here is going to be 0.11 kilocalorie per kilogram, and then 100 minus T final equals 0.075 kilograms times 1 kilocalorie per kilogram degrees Celsius, and T final minus 0. I didn't put degrees Celsius down here. So now let's distribute this through. This would be 11 times 0.05 would be, what's that? That's all right. I want to distribute twice. I want to clean it up. So let's put, what is 0.05 times 0.11? That's going to be 0.0055, isn't it? Okay, so let's take this up to the top to finish this. So 0.0055 times 100 minus T final equals 0.075 times T final minus 0. No. .0055. Yep. So this is going to be 0.55 minus 0.0055 T final equals 0.075 T final, right? That looks good. Now we'll leave this 0.55 on this side, throw this negative T final to the other side and add it, right? So we'd end up with 0.55. Then we're going to end up dividing it out, but it's going to equal to 0.075 T final plus 0.0055 T final. If we add those together and divide it out, this is going to be let's see, 0.005. So this is going to be 0.081, I think. Is that 0.081? 0.0805 would be T final. That should be the common T final. And what is that common T final?
6.8.
Ah, it works. Now for lab, you're actually going to have T final. You'll measure T final. We got it, right? Yep, that's final temperature. Yeah, I...
Well, look, I mean, I went into 3 other problems doing this thing. No wonder I go through 4 notebooks. So I know
Quit whining! What else we got?
Let's start with 1.
All right, let's move on then. Let's review what we did last time.
When I talk to you,
Let's review this one last time, because we're going to do a problem like this then. So here's what we looked at last time. And when you print the lab, make sure you only print pages 1 through 6 in the lab. So double check that. So here's what we looked at last time. If you're going to take ice at -40, there is a specific heat for ice. Change in temperature is going to be 40. Notice it doesn't take a lot of energy to heat up ice. Then you need to melt it. It's a flat line temperature because it is going to melt at the same temperature. It's going to start out at 0 degrees solid ice here. It ends at 0 degree liquid water over here. There is no temperature change in this. This is just the mass times, this is called the enthalpy of fusion, how much energy it takes to melt something. Yes, you'd have to be. Then you have 0 degree temperature liquid water. You got to heat that up to 100. Here you're going to have 100 degree water. That is going to be the mass of the water, specific heat of liquid water, change in temperature. In this case, the temperature change is 100. Then this long flat line here represents the fact that water is going to stay 100 degrees while you boil it away. And that is the mass times the enthalpy of vaporization. It takes a lot of energy to do that.
One of our questions is asking for how much energy it would take to get to 100 degrees Celsius steam. So do you only do steps 1 through 4? Or if it's
You stop right here, yes. Yeah, so if you're going to get 100 degree temperature steam, you're going to stop. No, let's see. No, if you get 100 degree temperatures, which one's that?
I think it's 14, 22, or no, 22. Right? Convert 2 kilograms of ice into a negative 45.
23?
Yeah.
Or is that
Yeah, so you have to
I think it's
23.
steam right to the steam.
So the last calculation would be the vaporization one?
Yes. Yep. Yeah, you'd stop. Yes. It's going to be this one right here. It's going to be your last one because you've actually boiled it away, so you should have steam at 100.
So if you said steam at 101, then
Yep.
5.
Then you're going to have to add 1 degree onto this and do this calculation. Steam at 101, you'd have to do this step here and make this 1 degree. Yep. Okay, so let's do an example like that, which is kind of over here. So, calculate the final temperature from phase change, cooling soda with ice cubes. Soda or pop? Huh? It's pop?
Coke or Pepsi? Or Mountain Dew?
No, that's in the South. Alabama, that happened to me. What do you want to drink? I'll have a Coke. What kind of Coke? Root beer.
No.
That's how they talk down there. You know that? Every drink's a Coke. What kind of Coke? Root beer. What kind of Coke? 7-Up. Can't make this stuff up. Okay. So, 3 ice cubes. We are going to chill this water with 3 ice cubes. So, better. We are going to have
Zoom out.
insulated container here. Beautiful drawing of my insulated container. We are going to drop in 3 ice cubes. Here's my ice cubes. Doop, doop. We've got 0.25 kilograms of pop at 20 degrees Celsius initially. Zero degrees Celsius ice. Here's what we're looking for. Find the final temperature when all the ice is melted. Okay. And we've got a mass of ice cubes are 6. Each ice cube is 6 grams. So we've got 18 grams. 0.018 kilograms. I guess we've got the ice. We've got that in kilograms. So we do the same thing. Q loss to Q gate. Now, what is going to gain heat and what is going to lose heat? What is going to gain heat? The ice, my water, is going to lose.
Yeah, I thought it was soda, man.
Soda,
Change it to pop.
well, pop, soda, we're going to assume it's going to be water, huh? Assume that the soda is kept in a foam, assume that the soda has been heat capacity of water. Now, so this right here, yeah, we better change this to soda. Good point. So, this is going to be our mass of our soda. Specific heat of soda. Mass soda. Pop would be a lot easier. Man.
Just S.
Now, here's what we need to do. We are going to melt all of this ice. Okay? So, first thing we're going to have to do is we're going to take the mass of the ice times the enthalpy of fusion of the ice plus, once that ice melts, then it will also heat up. We got to get a final temperature out of this.
How do we know how much is multiplied by the next step if we don't know the final
Well,
temperature?
at this point, once this ice melts, it's going to be, we're going to add this on. It's going to be liquid water, correct?
So liquid water at 0?
Yes. You're going to treat this right here as added water. Once this ice melts, it's going to be added water. Okay? So, this right here is going to be some mass of liquid water now. It is going to have a specific heat of liquid water, and this is going to be the change in temperature of our water. So all the ice is going to melt, and as that melts, it becomes part of added liquid water by only, I mean, it starts out with 0.25 kilograms. We're only adding 18.
Water and soda, but why?
This is going to be treated as, this over here is our starting soda. So this is going to be our 0.25 kilograms of our starting. We know that this right here is 0.018 kilograms of our ice. Then this right here is our melted ice. So once this melts, it is going to be liquid water. So these masses here are the same. Because as this ice melts and keeps melting, some of that turns into liquid water, and that liquid water that is melted is going to warm up as well. So this, let me put these in like this. My specific heat of my soda, if I use, we'll use this as water, and it says to assume basically it's water. This is going to be then 1 kilocalorie per kilogram degrees Celsius. Change in temperature of our soda. How am I going to put this in? Yeah, 20 minus T final. Point 0.018 kilograms, specific heat of ice. Specific heat of ice. And where's our chart for that? This is enthalpy of, excuse me, you're right, enthalpy of fusion of ice. Enthalpy of fusion chart is where? Right here. So enthalpy of fusion, well, it's going to be water. Kilojoules, what are we doing? We're going kilocalories per kilogram. So this is going to be in kilocalories per kilogram, 79.7. Kilocalories per kilogram. No change in temperature, correct? No change in temperature. This, of course, is going to be 1 kilocalorie per kilogram degrees Celsius. But how about our temperature change? So this is going to be T final minus 0. So we're going to drop our ice cubes in. They're all going to melt. Not only are they going to melt, but that added water is going to warm up as well. So when everything's done, we have no ice left. What temperature do we have? T final. Well, let's see if we can get this out of this. This is going to be 0.25. Make sure I've got the right units. Times 20 minus T final. What's the 0.18 times 79.7? 1.4346, and that's in kilocalories for units, but we should be all right. Yep, kilocalories. Yep, kilocalories. Plus 0.018 T final minus 0. No. 1/4 of this is going to be 5, huh? 5 minus 0.25 T final equals 1.4346 plus 0.018 T final. So we'll bring this to the other side. We'd end up with 5 minus 1.4346 equals 0.25 T final plus 0.018 T final. Right? $3.5654 equals 0.0268 T final. What do we get? When I worked this out before, I used different units. I hope this works out. What do we get? Oh, yes. Okay. We'll look at this other, we'll do one example of conduction here, and then we'll look at the lab a little bit. So, this diagram here is heat of conduction. And it's really molecular collisions. So if you take a, I don't know, piece of copper or whatever, and you're holding it on this end, uh-oh, here comes my drawing. There's your fingers around this end. Let's see, do you have enough? Too many fingers? I don't know. You don't need a thumb? Thumb's buried underneath there. You know, it makes sense. If you were to heat this on this end, how fast is it going to get to this end? Right? And probably how fast the heat is going to get to this end and how long you can hold on to it would depend upon the material. Versus, you know, copper, iron, aluminum, and so on. So there is a thermal conductivity, and that thermal conductivity is the K. So it's thermal conductivity of the material.
So if it's less conductive, is that energy somehow, or
It would just take longer. So this isn't a rate, this is actually in a rate of heat transfer in watts or kilocalories per second. So this could be in kilocalories. This is seconds. Then K is our constant here. Then it would make sense to have our surface area. D is the thickness of our material. And temperature change. So let me zoom in on this K chart. So what's going to conduct pretty fast looks like we get silver. These are the values we have at least. And I'm looking at the right side. This is in joules. What's the S going to be? Seconds. This is going to be meters, degrees Celsius. Because we've got thickness in here, right? We've got thickness. So it looks like heat's going to go through silver pretty fast. We got heat, copper, aluminum, steel, and so on. Obviously, if you can't transfer much heat at much rate, you're going to have an insulator at the bottom. And thermal conductors on top. What's going to keep your air gap? How do you create your air gap in a coat? You'd still have to have some kind of, what's that? Michelin Man suit? That would work. That would be good. You could probably sell that to the car industry too, because you could have a wearable airbag too, right? So let's see, did I do one example as all of this? I think I just did one example here. Heat transfer, that's a convection. Yeah, I think I just did. We'll just do one of these. When we do HVAC, we do a lot more, but let's just try one of these here quick. This is styrofoam box. So this is our area. This is our thickness here. So D is our thickness. So we got area, we've got D. And let's change that to meters. How many meters? .025 meters. The box contains ice, water, canned beverage at 0 degrees Celsius. The inside of the box is kept cold by melting ice. How much ice melts in 1 day if the ice box is kept in the trunk of a car at 35? And this would be doable, almost be doable as a lab. We could close up, we can get different coolers, right? Close them, measure out how much ice we have the next day or something like that. First of all, how much heat is going to flow into the box? How much heat flows in? So here's our equation from before. We have, this is our equation. Yes, yes. So we're going to put how much heat is going to flow in. So how many, we got 1 day, right? Into the box, kept at 0, how much ice melts. So this is going to end up being 35 degrees. So you got 35 degrees meters here. Yeah, we change it to meters. So the temperature difference here, this is our 35 degrees temperature difference. Yes, I got to double check on how I ended up calculating that. We're going to solve this for Q. All we're going to do is do everything here, and we're going to multiply both sides by T. Because then we've got everything. Now, here's the problem, though. A year. A day. 24 hours. We got 1 day here, correct? 1 day, how many seconds? One day, how many seconds? 24 hours. 1 hour, 3,600 seconds. So this is 86,400 seconds. So we've got 86,400 seconds here. 0.025 meters. We've got styrofoam. What is our value here for styrofoam? Yes. Does it give it to us in the problem? Do we have styrofoam on here? I have written 0.01. It doesn't tell us that anywhere. Crap. This right here, I'll have to look in our book. I have 0.010 joules per second meter degrees Celsius. 0.01. Yeah, somewhere it's got a, it must be in the book. It's not on our chart. So I was looking on our chart here. Yeah, this is just our constant for styrofoam. But you would think they'd have the dang thing on here.
Human tissue.
So, with our area is what here? Our area is 0.95 meters squared. So how much heat do we get out of this? All the units should cancel out. I got 1,150,000 or something like that. Is that right? Yes. What do we get? 1149. That's fine. 1149120 joules. Okay. Yeah, this right here, this change in temperature is the temperature difference between the inside and outside. It's 35 degrees. So now, all of this heat is going to go into melting ice.
So is that like finding equilibrium or something?
This temperature, that's just the temperature between inside and outside the container. That's the amount of joules that's going to go through there due to the temperature difference in one day. Because since you've got ice in there, it's going to stay 0 degrees on the inside. It should stay 0 degrees on the inside, but eventually, when you're adding this much heat, you're assuming you have enough ice that it all doesn't melt. So now we're calculating how much ice does melt. So all of that heat is going to go through the styrofoam. So now we're going to calculate what mass of ice melts. If this is in joules, how many joules per kilogram? Enthalpy of fusion of ice, we need that value as 333, I'm pretty sure. That kilojoules? So 33 kilojoules would be 333,000 joules. So if we divide this out, we're going to get kilograms, right? And our kilograms is going to be 3.45 kilograms. Okay. That's about 7 pounds of ice would melt. All of this heat that's going to flow through the styrofoam container is going to go into melting the ice. If you have more than 3.45 kilograms of ice in there, you should be fine.
Is that box big enough to hold up?
Oh, I don't know. With that area, it doesn't sound very big, does it? Okay. We are going to end this there. I don't have any other questions on the other stuff. So we end there. You don't have any questions beyond this. I want to talk about lab here for a sec. So sent you an email that has the lab. Okay, so here's the lab I sent you. Here's what we are going to do. There's our setup. So if we use a hot plate here, we have water. This is our metal sample inside boiling water. If this water here is boiling, what's the temperature it should be? 100 degrees Celsius, very, very close. Yes. What's that? Well, it turns to steam, but it should boil. If you're at atmospheric, it all depends upon what the pressure is. So we can boil water straight out of the tap if we put it in a vacuum pump. I'll have to bring the vacuum, see what we got for vacuum pump. But if this is boiling, this metal inside here, if you let it boil for quite a few minutes, should be at 100. Now, I'm going to bring nickel, copper, well, different metals. Then, you're going to take this test tube, wrap some paper towels around the top, because we're going to dump this metal into water. The temperature of this metal right here, is, and the thermometer should verify this, should be very, very close to 100. I'm hoping it's 100, because it's in boiling water. This is our calorimeter. Now, this is aluminum. This ring will go in here. This cup will go in here then. It's insulated with air. But this right here is going to have our water in it. So, not only are we going to heat up the water in here, we're going to heat up this aluminum cup. This black ring will go on the top of the whole thing. This ring right here will sit on top in that lid. This will fit inside this hole here. So when you dump your metal in here, again, you're going to heat up the water in here, and you're going to heat up this aluminum. We're going to keep this stirrer out. We can just swirl it. So there's two things it's going to heat up. So if I go into my equations here, this is our water. We're going to heat up the water. This is going to start out probably around room temperature 20. This calorimeter is the aluminum calorimeter. We're going to heat that up as well. Again, the water is inside the calorimeter. After it, whatever we get to the max. You're going to be able to, we'll put a, see this small hole right here? We'll put a thermometer through that. No, there's going to be very little loss. So, the water inside the calorimeter is going to gain heat. The calorimeter, the aluminum part itself, is going to gain heat. The metal is going to lose heat, correct? So here's what we've got. The heat lost by the metal here is going to equal the heat gained by the water and the aluminum cup, right? If you solve this whole thing, this would be the mass of the metal that's in the boiling water, the specific heat of that metal, change in temperature of that metal, and that's going to be 100 minus whatever T final is, right? You're going to measure T final for this. You're going to have it. We're going to calculate the specific heat of the metal for this. You're going to know how many grams of metal. You're going to know the change in temperature. You're going to know the mass of the water that's in the cup, specific temperature, or excuse me, specific heat of water, the change in temperature of the water. You're going to know the mass of that aluminum cup, the specific heat of aluminum, and the change in temperature of that cup. If you solve this for the specific heat of the metal, you can see it's going to be everything on this side divided by the mass of the metal and the change in temperature of the metal. Question? Because there's an air gap there, so it's not going to heat up. So this specific heat of the metal should match up one of our metals here, aluminum, lead, copper, iron, whatever I bring. I think there's nickel too. I think I've got a couple extras. It should match. Okay? Yes. Whatever metal you have, I'm hoping we get very close to this. So again, your metal should be about 100 degrees. We'll put some paper toweling around this test tube because you're going to dump it out. Dump the metal into the cup that has water in it. It's going to be this cup right here that has water in it. We're not going to stir it with this because that adds some more heat values. We can just swirl it by hand. We're going to use a thermometer. It'll tell you the temperature on here. We should be able to get to specific heat. There is a spreadsheet that goes along, but there's a good data table right here. Mass of water in the cup, mass of the metal sample, mass of the metal calorimeter cup, initial temperature, hopefully this is 100. The initial temperature of the water and the calorimeter, if you take it out of the tap, that should be about 20. You're going to measure it, right?
What was the specific heat? Do we want it in grams in that report?
What do I have it for units on this? Do I have the units in here?
Go back to the table.
No, you can use the specific heat in, do I have it here? I got everything in calories. So calories right here, calories per gram degree Celsius.
That's what your numbers were.
Yeah, it better have been. Yes. Calories per gram degree Celsius. So I'll bring a bunch of copper. That's just copper BBs, right? Those are easy ones. But we'll do different metals. We'll give you a couple. I don't know for sure, but lead sinkers would be another one too. I can just buy a bunch of lead sinkers. Would be pretty much, they're pure lead. But I think I've got a bunch. I've got some lead. So that shouldn't be too bad. It goes through this. There's some questions at the end to answer. I think there's 8 questions. There is a spreadsheet here. This is one with somebody's data in it, so we'll do the same thing. Percent error on this is, so I must have identified what metal here. I don't know which one they had point. We were supposed to get 0.215, so whichever metal's 0.215. I thought I got another one here that's got some of them on here. I'm going to look. There might be another spreadsheet. Darn it. I think I got an updated spreadsheet, but anyway, it should work out well. So print out the lab. I'll check to see if I have another spreadsheet.